Thank you everyone for joining us today in this webinar for dish preparation. Dr. Steve Levett, the Director of Clinical Applications at Cooper Surgical, will be leading the presentation. I'll hand over to Dr. Steve.
Thanks, AK. And we're going to talk today about dish preparation and how this underpins the whole embryology culture system, why it's incredibly important to get it right and to maintain a stable culture environment throughout the embryo's development. So we're going to cover a few factors here. We're going to look at laboratory factors that affect IVF outcome. We're going to look at the effect that pH can have on the system, some of the challenges that we face. What about contamination and air quality? Look at osmolality, the role of oil and how important that is, the drops that we use, the drop sizes, shapes, volumes, etc. And then just a summary at the end. And hopefully at the end of the presentation, you'll have an understanding of how important the dish preparation technique and stability is to the whole process. So on the next slide, you'll see that we have a publication done a few years ago now by Don Rieger at Life Global, who tried to put together an estimation of the number of factors that can influence the outcome in IVF. And as you can see, he came up with a number of 175. We don't know whether that is the exact number, doesn't really matter. What it tells us is that it's a complex process with many factors that are going to influence the outcome, and you can see some of them listed on the left here. If we go to the next slide, you'll see ones that are particularly relevant to dish preparation. So these are things that we need to consider. So we need to consider air quality. We need to consider where we're going to make dishes and at what stage, where they're going to be used in the lab. So this is not just about culture dishes. This might be to do with the dishes that you use for ICSI, the dishes used for denudation. So for culture dishes, we're going to work at room temperature, of course, but in some other instances, we're going to be working at 37 degrees. The culture media that we use can have an impact on stability. So the starting osmolality, for example, we're going to look in detail at pH and osmolality. We'll make some reference to temperature, the type of dishes that you use, the choice of culture oil, and not only the type of oil, but the volume, etc. And also related to air quality, we've also got to take into account the role of volatile organic compounds. So all of these things together all play a part in maintaining a stable culture system, and the dishes and the dish preparation is an integral part of that. So on the next slide, we're going to look at pH in particular. And I want to draw your attention to the two areas where pH stability is most profoundly felt within our culture system. pH is important throughout the embryo lifespan in the lab, but there are two particular areas where we need to take account of the role of the pH in the external environment. So as you can see here, denuded eggs. So when we've done the stripping of the eggs for ICSI, they become unable to modulate their internal pH. So they rely absolutely on the external environment. And that has a role in how we do the denudation process itself. And as you can see at the other end of the spectrum, we've got cryo warmed embryos nowadays with vitrification. They also lose their ability to regulate internal pH for about 3 to 4 hours after the warming process. And that has implications about where we put the embryos after we've done the vitrification. Question I'm often asked when I'm visiting labs is, should my warmed embryos go directly into embryo transfer media, or should I put them into culture media beforehand and then transfer them into embryo transfer media just before the embryo transfer process? What this demonstrates is that it's important, whatever you do, that the medium that the embryo goes into after warming is properly equilibrated and properly controlled for pH. Now, pH is an interesting concept because it's controlled absolutely in our culture system by the concentration of bicarbonate in the media and the concentration of CO2 that we provide in the incubators. And after all these years of embryo culture, we still don't have an exact target for the pH of our media. So we know that the pH of human embryos, excuse me, is around 7.1. So to avoid acidification, we set the lower level around 7.2. And we know that there are studies that have suggested that embryo development is compromised if the pH goes above 7.4. So most commercially available media set the limits of pH between 7.2 and 7.4. And that's actually quite a wide range. And we should be aiming for a more specific and stable pH in our system. And in most cases, when I'm visiting labs and doing pH testing, we want to set it at somewhere around 7.27, 7.28. That means that we're less likely to see the pH drift above the upper level of the range when we take dishes out of the incubator, and we're not running the risk of acidification, that the pH will be too low. So we don't know exactly what the target is, but what we need in our culture system is it to be 7.3 or just below, ideally, but stable throughout the development stages of the embryos in culture. And that's the key factor. And we have many stresses on the system that are going to try to change that pH and ultimately osmolality over time. Of course, the most important one is evaporation, which we need to be acutely aware of, not only making the dishes, but throughout the culture process as well. So on the next slide, we will see that one of the areas that I mentioned where pH is particularly important is at denudation, because this is where we remove the cumulus cells and then the eggs themselves are unable to control their internal pH. So they rely absolutely on the external environment. So when we're doing denudation, we need to ensure that pH, osmolality, and temperature are as stable throughout the whole process as possible. Of course, we have to wash the eggs after the denudation to remove any traces of hyaluronidase, and witnessing is key to all aspects of the embryo's journey in our lab. But just to stress here that the dishes that you make for denudation have to be appropriate for the time scale that you're going to use to do that denudation process. So the big temptation is, of course, to put a lot of cumulus oocyte complexes in one drop, and that might take a considerable amount of time to strip away the cumulus cells. So be aware when you're making those dishes to make them appropriate for the time at which you're going to be involved in the stripping process itself. And if it's going to take a long time and you're worried about temperature changes, and therefore, depending on the type of medium that you're using, you may get pH changes, or you're worried about evaporation, then put fewer eggs and cumulus complexes in each drop and do them sequentially rather than trying to do them all at one time. And that's equally the case when we're talking about ICSI on the next slide. So again, these dishes are going to be potentially exposed on our heated stage while we're doing the ICSI for a considerable length of time. So in this, just an example of how you might set up an ICSI dish, we're actually going to be using relatively small volumes of medium. So typically, you're going to use between 10 and 20 microliter drops. These are very vulnerable to changes with evaporation when you're making the dish. But equally, you've got to consider temperature during the process, because HEPEs and MOPS buffered medium control pH by temperature. And the dish, although it's on a 37-degree heated stage, it's exposed to the overall temperature environment within the laboratory, which is always going to be colder than that. So immediately you put the dish on the heated stage, you're going to start to lose temperature. And again, a stress to embryologists: don't overload your ICSI dishes with too many oocytes because over time that temperature change will affect the pH and could potentially affect the subsequent development of embryos. So be cautious. Don't think, oh, I can put 10, 12 eggs into a dish and that will remain stable throughout the time I'm doing the ICSI. That's probably not the case. And of course, the only way to truly know is to validate the process in your lab. And that means checking the temperature of those drops throughout the time frame that you're likely to be doing ICSI. So we've got the medium drops that are going to have HEPs or MOPs. We're going to have a PVP drop, which is less prone to evaporation, and then a drop with the sperm in. And we need to equilibrate the dish before we put our material in there, gametes. But equally, we don't need to leave them too long on the heated stage so that the temperature will change significantly, affect pH, and therefore affect your ICSI results. So it mentions here, ICSI dishes take at least 30 minutes to equilibrate. So that also means reusing ICSI dishes is problematic, because once you've had them on the heated stage, the temperature will have dropped. You put them back to re-equilibrate and they probably won't reach the correct temperature before you potentially want to use the dish again. So again, reusing ICSI dishes may not be the best way forward, and it's always better to make more dishes than rely on one dish being used over and over again. It also applies on the next slide if we're talking about some of the newer techniques. The next one relates to the Pixie dish. And you'll see here that it's set up in a slightly different way. But the reason I've highlighted this is not necessarily to talk to you about Pixie itself, but look at the volumes that we're using. So here we're rehydrating the hyaluron plaques with 5 microliters of buffered media. This is a very small volume and very prone to evaporation. So again, making these dishes up needs care and attention so that you get them done in the right way to avoid as much evaporation and potential change as possible. So if you're going to think about using Pixie as part of your sperm selection in specific patient groups, always think about how to make the dishes efficiently and make sure that they remain stable again throughout the time period you're doing the ICSI procedure itself. Okay, so denudation and ICSI, not necessarily culture dishes, but they still need care and attention, not only making them, thinking about the volumes that you're going to use, but also the length of time that they'll remain stable while you're doing those specific techniques within the lab. So we're going to talk now in the next few minutes specifically about culture dishes. If you just go back one slide, okay, please. Proper preparation prevents poor performance. It's a key factor when we're talking about culture dishes. Many embryologists who've got years of experience, when you start to talk to them about the making of dishes, tend to roll their eyes and think, is it truly important? But if you imagine nowadays, if we're thinking about uninterrupted culture, we're going to make a dish the day before an egg collection and potentially keep that dish in an incubator for 5, 6, 7 more days, then the dish itself and how you make it and the medium within it can have a profound effect on the outcome for the patients. And so attention to detail here is critical. So next slide, please. So what do we need to think about when we're making dishes for embryo culture? As I mentioned, we've got to think about whether a dish can be prepared to sustain pH and osmolality for up to 8 days. So a day before the egg collection and then maybe potentially 7 days in culture. Is that possible in today's embryology environment? In the past, with humidified incubators, that set its own challenges, but we also have to think about the new benchtop incubators, many of which are dry, including time-lapse incubators, many of which are dry themselves. So again, that has an influence on how stable the whole process can be. We'll talk about oil later, but we need to think about how we add the oil, how we add the drops. What difference does oil volume make to the outcome? And different types of oils may have different effects in different scenarios. Then, as I mentioned, we've got to think about the incubators themselves We always traditionally used humidified incubators, but there has been a move over the last few years to dry incubators, which have their own issues. They have some great advantages in terms of control, stability, but for evaporation, they provide a different environment that we need to be aware of and prepare our dishes accordingly. And then we need to think about the type of dish that we use. And right at the very end of this talk, you'll see what effect preformed wells might have on the potential for evaporation in the dish. So we've got some challenges. We need to have a very robust SOP to help us with dish preparation, and we need to stick to it. And when we look into labs and look at their protocol drift within their SOPs, we often find that the area that we see most drift is within dish preparation. So it's important that the SOP is robust, and it's important that it's adhered to during the whole procedure and not cut corners to make our lives easier, but make the lives of our embryos much more precarious. Okay, so what are the possible pitfalls of dish preparation? Contamination. Again, in the early days of IVF, when we were culturing in tubes, we didn't use oil. We used large box incubators that had trays of water in the bottom of them. We suffered horribly with contamination. The environment wasn't great. Our techniques potentially weren't great, and we didn't have any safeguard with the oil layer that we use nowadays. So contamination was always a big issue. It's not just from bacteria and fungal sources. We also have to think about contamination from VOCs within the laboratory. We have to think about the establishment and control of the osmolality, the pH and temperature. How long does it take to equilibrate? And how long should we use bottles of media? Should they be out of the refrigerator? Aliquoting, all these sort of things come into play when we're thinking about the challenges of making dishes effectively. And then the integrity of the microdrops. Should we use preformed wells in our dishes, or should we use a normal Petri dish? How are those plasticware treated? Are they going to allow drops to remain separate and intact, or are they going to be problematic? And one thing to point out here about culture dishes is that often the lids of the dishes are not treated in the same way as the body. So don't be tempted to use the lids for culture or any particular treatments like ICSI, because they may not be treated in the same way, and you may have problems using that. So we're going to move on to look at contamination. Again, this is mostly a thing of the past, but we always have to be aware of it. And we always have to be aware that we need to use the best sterile technique that we can. Within the embryology environment, it's impossible to use absolute sterile technique as you would in other areas, but we need to do our best to make sure we keep contamination risks to an absolute minimum. You can see these paper published a number of years ago now in 2007, but it reported that there were cases of contamination at around 0.7%. They were mostly Candida and E. coli. These were bacteria that were found in the semen samples, mostly of the patients that were coming forward. And we also found that a lot of these E. coli particularly were resistant to the antibiotics used at the time. So around that time, there was a change from using penicillin and streptomycin to now using gentamicin, which has helped as well. So we need to be careful when we're dealing with the material that we have, and we need to use the best technique that we can to minimize chances of contamination. So we've also got to think about VOC. So on the next slide, we're looking at air quality. You can see from this diagram on the right, which is a hugely blown up indication of what a HEPA pore looks like within the filter, and the VOC molecule in the center. And of course, it just passes directly through the HEPA filter. So in terms of VOCs, HEPA filters are not sufficient. We need them in the lab to take out particulates, but for VOCs, we need specific filters to help us. The workstation filter air is working if it's switched on, and it should be during dish prep, and we'll talk about that later. But we should also be working in a decluttered environment. And it goes without saying that we should always have inline gas filtration in our system. The most contaminating thing that comes into the embryology lab is the compressed gas. Regardless of the grade that you buy, the way that the cylinders are filled and processed always leads to some contamination. And in the bar graph on the right, you can see before and after filtration with an inline filter that the inline filters are very efficient, with the exception of acetone, very efficient at removing VOCs. And in all cases, including your equilibration incubators, inline filters are critical to keeping VOC levels to an absolute minimum and minimizing the impact that they may have over time on your culture system. So we then need to think about ourselves in the lab and the use of PPE. This became acutely in focus during COVID, and we changed many of our protocols. But as you can see on the slide, we can only really aspire to clean technique. We'll never work with aseptic technique because the embryology lab doesn't allow us to do that. But adequate training in the best techniques is important. How we clean the lab, when we clean the lab, what materials we use can also play a major part. And the use of ethanol or IMS should be avoided at all times during the working day. You can use it at the end of the day, but certainly not during the working day. And what PPE should we work with? Ideally with scrubs and sleeves, but this is rarely seen. We often have scrubs, but most of them are sleeveless. But again, in an ideal world, this would be something that we use. And theatre hat and mask generally recommended. And do we wear gloves, or just do we ensure that our hands are washed thoroughly? Most people would recommend that you use nitrile gloves while you're making medium and making the dishes. But if not, very effective and thorough hand washing is important. One of the things of note is when you put your scrubs on in the morning, these don't protect you throughout the day if you go in and out of the lab. So be cognizant of that. They're not a protective barrier. They're only there to help you. And again, use of scrubs, use of gloves, etc., only work effectively if you use them in the right way. So just to follow on from that, off-gassing is important with the plasticware that we use. Most plasticware that we use in IVF is made of polystyrene and therefore can emit styrene when you open a pack of dishes. Every embryologist will know there's a very distinctive smell. So dishes should, in most cases, be off-gassed before use. The period of off-gassing can be determined using a VOC meter if you have one. And again, the correct VOC meter, some of the meters on the market only count down to parts per million. In an embryology lab, we need to have a meter that will count down to parts per billion. And we can refer to the Cairo consensus to give us some limits here. Off-gassing should ideally be done in a laminar airflow cabinet outside of the main embryology laboratory, because of course, when you're off-gassing VOCs, if you do it in the main lab, the VOCs go into the general lab atmosphere. Some dishes do have this gas permeable membrane or packaging that allows reduced off-gassing time when you get them into your lab, because they're off-gassing the whole time they're in transit. We're lucky that because of the way we culture now in reduced oxygen, this may reduce the possible toxic effects of VOCs. So in the future, we may go down to even lower oxygen tensions than we do now, but they do help in the control of the effects of VOCs, not in the VOCs themselves, but in their potential effects. So don't ignore VOCs. They're important to control in the first instance. And again, when we're talking about oil is not only protects you from evaporation, but it also protects you from the accumulation of VOCs. So again, we need to be cautious in whether we think we should replace oil in the dishes or not. And we'll talk about that in a little while. So one of the ways we can mitigate the accumulation of VOCs into the oil and the stability of the culture system over time is to think about whether we should change the medium on any particular day. So if we look at the bottom here, the sequential media had two distinct media types, the cleavage media and the blastocyst media. So we had to change that media on day 3 when the embryonic genome was being activated. So here, of course, by changing the medium on day 3, we reduce the risk of the effects of long-term effects of evaporation and also the accumulation of VOCs in the oil that we're culturing. You can use single-step media in exactly the same way. So you can use it and change the medium on day 3. We traditionally do it on day 3 because of its link to sequential media, but there's actually no reason to do it day 3. If you choose to do it on day 2, day 4, that's fine. I would always recommend changing the medium on day 5 if you have embryos still in culture and you've got early blastocysts that you want to go on to day 6 or day 7. In my opinion, the chance that a culture dish will remain fully optimal over the whole time frame up to day 7 when you've made the dish the day before egg collection is highly questionable. Those embryos are already compromised, and therefore we should be thinking carefully about changing media on day 5 if we're keeping embryos in culture. In an ideal world, we want to go to uninterrupted culture, but we need to be sure that our system will accommodate that and we're not doing more harm by changing the culture environment, excuse me, which outweighs the benefit of keeping embryos undisturbed. Now, this is a very telling paper from 2015 that shows the effect of oil volume on the stability of the culture system. So the 2 cells on the left are not magnified because it's quite clear to see there's a difference in volume between cell B and cell A. So cell B is as it was set up on the day 0, and cell A is after 7 days of culture at 37 degrees. And you can quite clearly see there's a difference in volume here. In the cells on the right, they've been magnified because it's very difficult to see any difference in the volumes in the 2 cells. Again, B as it was set up, and A after 7 days in culture at 37 degrees. The only difference between the cells on the left, the cells on the right, is that the cells on the left had 35 microliters of mineral oil as an overlay, and the cells on the right had 50 microliters. If you look at the table above and see the impact that that change in oil volume had, the pH rose from 7.2, which we was our starting point, to 7.29. But if you look at the change in osmolality because of the evaporation, very little in the cells with 50 microliters of oil, but with 35 microliters of oil, we've got an almost 100 milliosmol per kilogram change over that 7-day period. And bear that figure in mind when we move to the next slide. So this is a paper done by Jason Swain looking at the impact of osmolality on development of mouse embryos. Now, we've always got to be cautious when we compare mouse with human, but what it clearly shows in the mouse model, at least, is that rising osmolality has a negative impact on embryo development. And as you can see, as we get up to above 300 milliosmoles per kilogram, the impact on embryo development is quite devastating. So I want you to remember that 100 milliosmol per kilogram change that we saw in that previous slide. Most culture media that's commercially available has a starting osmolality of about 260 milliosmoles. So if over the time frame that we're talking about, 7 days, we get an increase of 100 milliosmoles, we're going way above this and potentially going to cause significant impairment of embryo development. So again, stability over time is as critical as the initial setup of the dishes, and we need to be aware of that. So does how the dish is set up have an impact? And again, we can go to the next slide and we can see quite clearly from, again, Jason Swain around the same time, showing that how you make the dish and under what conditions and certainly what volume you use can have a big impact. So unsurprisingly, if you make the dishes at 37 degrees, you get a significant increase in osmolality as you make the dish. So these are tested immediately after. So these aren't in long-term culture. These are just looking at the impact you have when you're making the dishes. So at 37 degrees, you get a significant increase in osmolality, as you might imagine. Interestingly, airflow doesn't seem to make too much of a difference. So we need to be aware that we need to keep airflow on and the flow cabinet uncluttered to maintain sterility, because of course that's an equal factor in our minds. How you apply the drops and the oil can also have an impact. So these are two different ways of introducing the medium into the dish. On the right is the standard method. So we put drops in the dish, we cover them with oil, and then we equilibrate them. On the left, the wash drop is putting drops into the dish, covering with oil, removing those culture drops and replacing them with new ones. So that's an underlay method. So that can help in a busy clinic with lots of dishes to prepare. It can be a pain to make so many in that manner, but it is worth considering when you're thinking about how to do dish prep effectively. One of the key factors, though, is volume. So as you decrease the volume, you increase the surface area to volume ratio, and you increase the risk and the rate of evaporation. So you can see here, there's a huge difference between using a 10 microliter drop, 20 and 40. So again, in our culture system, don't be tempted to use too small a volume in your embryo culture system, because remember, it's got to stay stable for a very long time, and therefore cutting the volume down can have a huge negative impact. So volume is important, not only of the culture medium that you're going to add to your dish, but also of the oil. And we're going to go on and talk about oil in the next slide. So don't overlook oil. As I mentioned, in the early days, we didn't use oil in our culture. We used open culture with larger volumes, but we still suffered with osmolality changes, I'm sure, and therefore pH drift. So oil is critical, and getting the correct type and volume of oil in your culture system is critical to success. It minimizes pH shift, it prevents changes in osmolality, as we've mentioned, it reduces temperature fluctuation by acting as a heat sump, and of course it's also a physical barrier that helps prevent contamination and also the ingress of VOCs towards the medium drops. And the mantra for embryologists should be, we use the maximum amount of oil in a culture dish without causing problems. So without overloading the dish so that you get the lid sticking or you get spillage. But our mantra should be, we use the maximum amount of oil in whatever culture dish we use, not the minimum. And where volume is restricted in some time-lapse cells, for example, then we might consider which type of oil we use, whether we use a lower density, lower viscosity oil or a higher one. In most general culture systems, volume is the most important factor, not the type of oil, although it may be protective in some circumstances. Okay, so if we look at the next slide that Dean Morbeck did at the time, the type of oil can also have an impact. So he published this article now almost 15 years ago. And you can see that washing oil generally has a beneficial effect. Whether you use it in water with medium plus protein, they all have a significant improvement in blastocyst formation rate compared to unwashed oil. So again, the type of oil and how it's processed, how it's tested, may also be something to consider when you're deciding which culture oil to use in your lab. So we're going to look at a more realistic setup now in the next slide. So this is some internal data, and these are more likely the scenario that you might find in your lab. So 20 microliter drops, and in the blue bars, 4.5 milliliters of oil, and in the orange bars, 6 mils of oil. And you can see these are in a normal dish that we might use with a single step media using paraffin overlay, and the dishes were prepared at room temperature with the airflow on, and osmolality was tested after the time frames that you can see on the graph. So out of the bottle, as I mentioned, around 260, 265 milliosmoles. After 5 minutes, we've already seen a rise, and you can just about make out that the lower volume of oil is causing a greater rise than the larger volume. But over time, of course, that situation gets worse. And so it's quite clear that the more volume of oil that you use, the better protection you're going to have to your system. And of course, changing osmolality is cumulative. These are separate dishes tested at different times. But if we used that dish that would set up for 48 hours, sampled it, and then sampled it a few hours later, we would see a consistent rise. Osmolality can only increase because we're not adding anything to the media. We're only observing evaporation. So therefore, it's going to increase dramatically over time, and we can't reverse it in our culture system unless we change the dishes and use fresh medium. So think about the volume of oil that you're using in the dish that you're preparing. And then the next slide, we just have a rule of thumb. So I've seen embryologists looking to see whether the oil just covers the top of the drops, but ideally we need a 2 to 3 millimeter thickness of oil above the top of the drop to give maximum protection. So again, don't be tempted to cut corners, to think about reducing the oil volume and trying to culture your embryos for significant lengths of time, because it will almost certainly introduce some risk and potential problems for embryo development. We did talk about different types of oil, and this is just a graph showing the protective effect of different oils that have different densities, and you can just about make out that some of the more dense oils can have a more protective effect. It may be that if you have a particularly vulnerable environment, you have a very low relative humidity in your lab, you're using a dry incubator or a time-lapse incubator that's dry, where the volume of oil that you can use is compromised, then it may be worth considering using a heavier oil in some circumstances. Even if you don't use them for other times of the year or for other processes, for long-term cultures, it may be appropriate to think about a heavier oil under certain circumstances. So again, there's no one rule fits all, not one answer to every lab. You have to look at your own system and determine how stable it is and what you might be able to do to help it. But thinking about the type of oil that you use can be one area where you might see some improvement. Of course, the different oil that you use will have an impact on equilibration times, and this is something not to be ignored. So the time of equilibration will depend on the surface area, the oil overlay, the type of oil, the volume of oil that you use, the type of dish, the starting pH, and the set point that you need. A publication in 2008 suggested a minimum of 10 hours for equilibration in most cases. That's now generally accepted that it's perhaps a little bit longer than that. So somewhere between 14 and 18 hours to get true equilibration is probably where you need to be. And just as an aside, if you want to make dishes in an emergency, so if you're using pre-equilibrated oil with pre-equilibrated medium and you want to make a dish to use, it will still take 4 to 5 hours to reach true equilibration. So always better to make more dishes the day before than try to make dishes in an emergency, because you probably won't get them to full equilibration before you need to use them. Okay, so we're getting towards the end of the talk about dish prep and how you can influence outcome. One thing I would like to just mention here is it's not only about the volume of medium that you use, the drop sizes that you use, the oil that you use. It's also how you make the drops. And this is a very nice example drawn up by Dave Morrill, one of my colleagues, that show the same volume of medium put into a dish or a different type of dish in different ways. So if you look at the top left, a drop like most of us would probably have made in the past, and you can see the surface area is 52.2 millimeters squared. The same volume put into a dish on a more flattened profile increases the surface area by almost 50%. So this encourages evaporation by doing it in that way. One thing to consider is potentially to using preformed wells in your culture dishes, because this then reduces the surface area to volume ratio with the same volume of medium. So here the surface area is much lower, and therefore the risk of evaporation is much less. So it's also about technique and how you put the drops into your dish, or whether you use dishes with preformed wells. Again, something to look at in your system and determine whether there are changes that you can make that might just make these small increases in your success over time. And all of them can cumulatively potentially make a big difference to your patients. Okay, so again, towards the summaries now. So I like this quote a lot. So if you just go back one slide. Spectacular achievement is always preceded by unspectacular preparation. So dish preparation sounds really boring. Sounds like it's something we always give to our most junior colleagues in the lab. But if you wanted to negatively impact the outcome for everybody in the clinic, and of course more significantly for the patients, just make dishes incorrectly, you won't get perfect embryo development in your system, and you will negatively impact the patient's chances of success. So just in summary, be scrupulous with cleanliness, including, I would always suggest the use of gloves. Not many people would use sleeves, but again, if you have them. This includes air quality. We leave the airflow on because we want to ensure sterility as much as possible. And it's shown by the papers that have been published to have little impact on evaporation at that stage. Be aware of possible effects of reusing open bottles over extended periods. Also, aliquoting, etc., can have a negative impact. You need to understand whether the plasticware that you use needs to be off-gassed and for how long, and that needs to be validated in every setup in every lab. Osmolality can change throughout culture, but it can also change during the setup of the dishes. So again, need to be aware of that when you're making the dishes, how you make them, and make sure that that's done effectively, and not use a heated stage, do it at room temperature. That's critical. And then the next summary, consider that underlay method. So where you put the drops in under the oil where a drop has already been, that helps with reducing evaporation risk. Don't be tempted to use too small a drop for your culture, because if you do, you need to take extra precautions, and you need to test your system to make sure it remains stable throughout the whole time frame. The rate of change of osmolality is influenced by that surface area to volume ratio that you saw. So think about how you make the drops, what profile they have, and think about whether it's worth investing in using dishes with preformed wells. The mantra should be for us, use maximum amount of oil where possible in every dish type that we use, and ensure that we allow enough time for full equilibration. That can, of course, have an impact as well, both in ICSI dishes, in making emergency dishes, and in trying to ensure that when you put a dish back in the incubator, you're giving enough time to get back to full equilibration. And I think the final slide just is some references. They're available if anybody's interested. They just try to demonstrate that we've, as far as possible, tried to use evidence-based to put the webinar together. And the last thing to say, of course, is thank you for listening. I hope you found some of the information useful. hopefully you can take it away and think about whether it can help in stabilizing your culture system. And always have at the back of your mind, dish preparation is not boring. It's not something we shouldn't be taking great care with. And if we do it properly, it can help give us the best quality embryos and give our patients the best chance of success. So thanks again for your time. Apologies again for the technical difficulties at the beginning. Thank you, AK, for advancing the slides for me. And we're almost on the hour, but if there's any quick questions, I'm happy to answer them. If not, I can always answer them by email or whichever way people want to contact me.
Thank you, Steve. I think we have 1 minute to take a few questions. If someone have any question, please you can put it in the Q&A. If we don't get back to you directly now on the call, we could always get back to you with the answers later on. I got 2 questions that from the Q&A. I could quickly ask you one of them. So one question says, how long does it take for the dishes to off-gas? Would an overnight be enough, or would you recommend a longer period?
Yeah, generally we recommend 24 hours, but it does depend on the type of the dish, the packaging that it's in. What I would say is don't be tempted to load the back of the flow hoods, the flow cabinets, with hundreds and hundreds of dishes. Try to do them on a regular basis and just have the ones in there that you need, because although I mentioned earlier that it's better to do it in a laminar flow outside of the main embryology lab, most labs don't have that luxury, so they have to do it within the main lab, and you don't want to have lots of plasticware cluttering up your work surfaces and your flow hoods, and you don't want to produce lots of VOCs into the lab if you can help it. So the general advice is 24 hours for off-gassing, depending on the type of dish that you use. As I mentioned, some do have a porous part to the packaging, which allows off-gassing while they're in transit. And of course, in that scenario, they need much less time. And remember, of course, as soon as you take your dish and put it into an incubator at 37 degrees, it will produce an excess of and release excess VOCs if you haven't fully off-gassed.
Thank you, Steve. I know we're exactly at the hour, but there is one more interesting question that I'll pass to you. It's asking about the best protocol to wash oil inside the lab.
Yeah, I mean, ideally, I think if possible, buy pre-washed oil, because that's under control of the manufacturer. If not, we used to use 600 ml Falcon flask, or you can use smaller ones, and put the media and the oil in there, rotate the dish a few times, let it settle in the refrigerator, and then take your oil from there. But in an ideal world, if you can, much better to buy the oil that's already washed, because when we try to do anything like that in the lab ourselves, it's very hard to validate it and to know whether we've done an efficient job. Whereas, of course, if it's done commercially, then those oils are tested and we know that they're as safe as they can be.